Hello friends, I welcome you in lecture number 8 on complex integration. In this lecture also we will discuss one more problem on contour integrals. Now before going for that problem, we just recall that suppose we have circle in the xy plane or complex plane whose center is origin and radius is r, then we know that we can represent this circle in parametric form as z equal to r times e raised to I theta, and if we are considering whole circle, then theta lies between 0 and 2 pi. But suppose we have circle with center which is different from origin, then that circle can be written as absolute value of z minus z0 equal to r, where z0 is center of the circle and r is the radius of the circle. So if we have a circle whose center is z0 and radius is r, then also we can represent it parametrically. Here if we have absolute value of z equal to r, then we write z equal to r e raised to I theta. Here instead of z we have z minus z0, so we will consider z minus z0 equal to r into e raised to I theta, and therefore z becomes z0 plus r into e raised to I theta, and theta is in between 0 and 2 pi. So whenever we have this type of circle whose center is z0 and radius is r, then also we can write its parametric representation easily, and for that we are following this. If we have mod z equal to r, we write z equal to r e raised to I theta. So if we have mod z minus z0 equal to r, instead of z here we will write z minus z0, and we will obtain this parametric form. So this we are going to use in this lecture. In our problem we have taken our contour as the circle of radius r and center z0 and in counterclockwise direction, and function is z minus z0 to the power n. Here n is any integer, z0 is constant, and we are integrating this function z minus z0 to the power n along the circle whose center is this z0 and radius is capital R. That is, we are integrating along arbitrary circle. We have any circle with center z0 and radius r. Suppose this is the center z0 and radius is r, so we are integrating along this boundary. So we are integrating along any circle whose center is z0 and radius is r. So method is same. First we have to represent our contour in parametric form, and then we will write z minus z0 in the form of single variable, which we will consider as our parameter in the representation of circle. So first we write that given contour is any circle with center z0 and radius is arbitrary radius denoted by capital R, and that circle we can write in this way also, absolute value of z minus z0 equal to r. So we can represent this parametrically. If we consider theta as parameter, then parametric representation of this circle is, we take z minus z0 equal to r into e raised to I theta, and therefore z is z0 plus r into e raised to I theta, and we have to integrate along the whole boundary of the circle. Therefore theta is from 0 to 2 pi. Suppose we start from this, then we integrate along the whole boundary of the circle, and here z0 is constant, and we will replace this z minus z0 in f of z by r into e raised to I theta, and we will require dz by d theta also. Here now z becomes function of theta only, therefore we can write derivative of z with respect to theta. z0 is constant, therefore its derivative with respect to theta is 0, plus r constant, derivative of e raised to I theta is e raised to I theta times I, and this is r into I into e raised to I theta, and therefore we will replace dz by r I e raised to I theta d theta. So this is our dz, and we will replace z minus z0 by r into e raised to I theta in this integral. So now we can convert this in the form of theta. So let me write here. So therefore given contour integral is z minus z0 to the power n dz. This becomes limits of theta are from 0 to 2 pi. This z minus z0 is replaced by r into e raised to I theta whole power n, and dz is r I e raised to I theta d theta, r into I e raised to I theta d theta. So now this complex line integral or contour integral is converted into real integral, in which variable of integration is real variable theta. Now we can simplify all these things. We take nth power of r and e raised to I theta, that is r raised to n e raised to I into n into theta, and this as it is r I e raised to I theta d theta. And now we can observe that r raised to n into r, that is r raised to n plus 1, it is independent of theta, so we take it outside integral. This I is also independent of theta, and inside the integral we have 0 to 2 pi, and we can combine this as e raised to I into n theta plus I theta integral with respect to theta. And now these are simple calculations. R raised to n plus 1 I, we can take here again, we can take I into theta common. So if I take I into theta common, or I can simply, okay, I take I into theta common, so I n plus 1 theta. So I am rewriting in this way. This is I n theta, this quantity, plus I into 1 into theta. Because I want to integrate with respect to theta, I write in this form. And now I integrate. Here I have r raised to n plus 1 I integral of e raised to n theta is e raised to n theta divided by coefficient of theta, which is n. Here instead of n we have I into n plus 1, so we will divide by I into n plus 1, and we keep this as it is, I into n plus 1 into theta, and limits of theta are from theta equal to 0 to theta equal to 2 pi. So I have applied this integral formula. E raised to n into theta has integral e raised to n theta divided by coefficient of theta. Here coefficient of theta is I times n plus 1, so I have divided by this coefficient, and I keep this as it is in the numerator. Now you can see this will create a problem for n equal to minus 1, because it becomes 0 for n equal to minus 1. So this is valid when n is different from minus 1. For n equal to minus 1 we have to integrate this separately, because n is any integer here, so n can take -1 value also, and for -1 this becomes undefined. So this is valid if n is different from -1, and this I will get cancelled with this, and these limits are for theta, so I can take this r raised to n plus 1 divided by n plus 1. This n plus 1 can be taken outside. Here I put theta equal to pi first, so I will have theta equal to 2 pi, so I into 2 pi into n plus 1, and minus for theta equal to 0, we have 0 into this, that is 0, and that we can directly write as 1 also. E raised to 0 is 1, and again this is valid if n is different from -1. So now we can simplify this r raised to n plus 1 divided by n plus 1, and you can see here we can apply Euler's formula. So we know that Euler's formula is e raised to I alpha can be written as cos alpha plus I sin alpha. Here instead of alpha we have 2 pi into n plus 1, so that I write here cos 2 pi n plus 1 and plus I sin of 2 pi into n plus 1, and this -1 is already there. And now we have to decide these values, and we can write this cos of 2 pi into n plus 1 equal to, we can rewrite this as cos 2 times n plus 1 into pi, and because n is integer, n plus 1 is also integer, and this is also integer, so we have integer multiple of pi here. 2 into n plus 1 is integer because n is integer, and we know that for cos function, if n is integer, we have cos n pi is -1 to the power n if n is integer. So here 2 into n plus 1 is integer, therefore we can write this as -1 to the power 2 into n plus 1, and because I have 2 here, it is square of -1, and that will give me 1. So this quantity is 1. And for sine function, we know that if we have integer multiple of pi in sine function, then it is always 0. So what is integer multiple here? Here n is integer, therefore n plus 1 is integer, 2 is also integer, so 2 into n plus 1 is integer, therefore we have integer multiple of pi here, so this becomes 0, this becomes 1. So let me write this r raised to n plus 1 divided by n plus 1, and I will have 1 plus 0, and this is -1, so this will get cancelled and we obtain 0, but this is valid for n which are different from -1. So what we have obtained, that integral of z minus z0 to the power n with respect to z is 0 if n is not equal to -1, and for n equal to -1 we can start from this. We can give this number 1, or we can give this also number 1. Suppose I give this number 1, and I will take n equal to -1 in this equation, and I will simplify. So for n equal to -1, so we write in this way, taking n equal to -1 in equation 1. In equation 1, left hand side is integral of z minus z0 raised to n with respect to z, and here n is -1, but we keep this as it is left hand side, and in right hand side we put n equal to -1. So this is going to be r to the power -1, and this r is already there. This is going to be e to the power minus I theta, and I have e raised to I theta here, so I can combine these two, I can combine these two, I can multiply these two. So you can see for n equal to minus 1, this is r raised to minus 1, this is r raised to 1. So if we combine these two, I will have r raised to 0. Similarly, here also e raised to I theta minus I theta, that is e raised to 0, which is 1. So we are left with I only, I into d theta, and we can integrate it with respect to theta. I repeat again, here I am taking n equal to minus 1, so here I obtain r to the power minus 1. I have already 1 r here, so if I combine these two for minus 1, I will have r raised to 0, that will give me 1. So I cancel this, that is going to be 1. For n equal to minus 1, this becomes e raised to minus I theta, and this is e raised to I theta. So if I combine these two, I will obtain 1. So I am left with I and d theta. So that I am writing directly here. Here I will have I and d theta, and integral of 1 with respect to theta is theta I is constant. So I have taken I outside, and for theta equal to 2 pi I have 2 pi minus for theta equal to 0 I obtain 0. So I will obtain 2 pi I if n is minus 1. So if we combine what we have obtained, that if I have integral of z minus z0 to the power n with respect to z, then it is 0 and 2 pi I. I obtain 2 pi I if n is minus 1, and I obtain 0 if n is not equal to minus 1, and in both the cases n is integer. So we have obtained this result. This is nice result, that if you have integer multiple of z minus z0, and if you are integrating with respect to theta, then you will obtain 0 for any integer different from minus 1, and for n equal to minus 1 you will obtain 2 pi I. And you can write for n equal to minus 1, you can see that if I take n equal to minus 1, I have z minus z0 to the power minus 1, that is 1 upon z minus z0 dz, and what I obtain 2 pi I. So they can ask this separately also, they can ask you to find out value of this integral also. So method is same, you have to start with this parametric representation of circle, which is r into e raised to I theta, and accordingly you have to convert everything in terms of theta, and you will able to prove this for n equal to minus 1 separately also. So for n equal to minus 1, you can directly start with this by putting n equal to minus 1, and method is same. So sometimes they can ask you to prove this integral also. Integral of dz over z minus z0 is 2 pi I. z0 is any constant, so if I take z0 equal to 0, then also I will obtain integral of 1 by z over this circle is 2 pi I. And but this is important, this is along this circle, boundary of the circle, whole circle with any center z0 and radius r. If you are changing your contour, you can get different answer. So this is very nice example, and we stop here, and we will continue in this lecture series in upcoming lectures. Thanks for watching.